Hello everyone, today what we are going to look at is the solution to today's LeetCode problem of the day, maximum fruits harvested after at most k steps. So this is a hard problem, but we're going to make it really easy and look at how to solve it. Okay, to explain the problem, it's a very simple problem. In this problem, we are standing on an infinite number line and our initial position on this number line is represented by this variable start pause, and here it is 5, right? So you can see the person standing at position 5 here. So that is our initial position. So there are also two other variables here. One is fruits, which is it's a 2D list which represents where the fruits are in the number line and how many of that particular quantity is present at that position. For example, here we have in this 2D list 2, 8. What this means is there are fruits at the position 2 in this number line, and there are 8 quantities of this fruit. And 6, 3 means in the position 6 there are fruits and there are 3 quantities of that fruit, so on and so forth. There's a final variable k which tells me what is the maximum amount of steps that I can take on this number line, and what is the final question here, how many maximum fruits I can collect from this number line uh, within k steps or with at most k steps, right? So at the offset this problem is very simple, right? So all you have to do is, okay, so k is equal to 4 here. So you can take 4 steps to the left, and that would be one possible solution for you. And you can see how many fruits you can collect just by taking 4 steps to the left. Or you can take 1 step to the left and 3 steps to the right. Or you can take 4 steps to the right. And so on and so forth, right? There are many, many combinations here, right? Or you can even take 1 step to the left, then 1 step to the right, and so on and so forth. But that is a very terrible strategy, like just zigzagging all the way around, which is something that you not prefer, right? Now, because k is a very small value here, you might think that, okay, why is it hard to just use all the possible combinations of k and just add up all the fruits and I'll give the answer, right? But in this problem, the maximum amount of k can go up to 2 into 10 to the power 5. So it's really impossible for you to generate all the possible combinations of k and then go over this list and add up all the fruits, right? So we need a better strategy to solve this problem, and that's what we're going to look at today. It's very simple, but we just need better strategies. Okay, now before we even dive into the core logic of this problem, I want to give you some insight here. In this problem, the value of k is not really that important, like the number of steps that you're taking, but it's actually the positions of fruits that are very important for you. And I'll tell you why right now. So here we have the value 2 and 5, right? So here, let's say I take 1 step from 5, it doesn't make a difference. If I take 2 steps from 5, it doesn't make a difference. But if I take 3 steps from 5, it really makes a difference. And if you see for all these steps, right, it's a different number of steps. So like theoretically they should make like different importance, right? Like because 3 is much greater than 2 and 2 is much greater than 1, so you would think the number of steps really make a lot of difference, right? But it's actually not. Why the step count 3 is much more valuable than step count 2 and step count 1? It is because a certain fruit is located at 3 steps away. So it's not the number of steps the number of steps that matter, but it's actually the position of fruits that decide the solution to this problem. So we're not going to think about this problem in the terms of how many steps we're allowed to take. We're just going to look at the position of the fruits, and then we're going to collect a certain number of fruits. And then what we're going to say is, while collecting a certain number of fruits, have the steps I have taken, is it less than x? Okay, is it less than k or not? So we're not focusing on the taking number of steps based on the k value, but we are going to just collect the fruits and see, while collecting those fruits, have I just taken k below k steps or above k steps, right? So that is going to be our core understanding of this problem. Don't concentrate on the number of the k threshold, concentrate on the fruits. With that in mind, let's look at the first way how we can make this problem very efficient, right? So this problem is always going to involve a lot of summing, right? So the final question is, you cross a certain number of fruits, and what is the maximum amount of fruits you can pick up? So to take the maximum amount of fruits, you will be summing all the individual location fruits, right? So for example, if I travel from 5 to 8 here, so I'd be adding 3 and 6, right? If I travel from 5 to 8 and all the way back to this 2 location here, so I'd be adding this, this, and this. So this involves 3 additions, right? And you can imagine that if it's a very big number line and there are lots of fruits, you would be adding those many fruits for those many times, right? If you're crossing 1,000 fruits, you're going to add this operation 1,000 times, right? But is there a better way to add all those 1,000, like no matter what, if I'm crossing 3 fruits, 5 fruits, 100 fruits, 1,000 fruits, a million fruits, is there a way where I can just simplify this operation and just use an add or subtract operation just once and get the answer like real time? It might sound very impossible, but there's actually a way we do this. So what we do is we initially add up all these fruits, and then while we are going to check, we are only going to do the subtraction operation once, and I'll show you how. So this concept is called prefix sum, and it's a very popular concept when you have to work with ranges, and more precisely when you have to add up all the values in the range, or tell from this, in this range, starting from this point to this end point, what is the sum of values, right? How do we generate this prefix sum array is very simple. So the first rule of a prefix sum array is that it will contain like one more index. So there are like many ways that this prefix sum array works, but just one implementation, a very simple one. So it will contain one more index than what you're trying to add up, right? So we have, let's say, a fruits which has 3 values. So prefix will have like 4 values. Okay. The second one is a very simple rule. So ps of I plus 1 is equal to ps of I plus v of I. So v of I is the value at that particular index. Okay, you just look at how this works now. So ps is equal to, and the first value in your prefix sum array will be 0. So prefix sum is prefix, that means up to that particular point, what is the sum of values I've encountered so far. So prefix sum of the 0th location will obviously be 0, because before 0 I have not seen an element, right? So that'll obviously be 0. Now, okay, now let's deploy this prefix sum algorithm, right? So ps of 1, 2 and 3, right? So prefix sum of 1 is equal to prefix sum of 0 plus v of I. So here we have 0, 1, 2. So prefix sum of I plus 1 is equal to ps of I plus v of I. So prefix sum of 1 is equal to prefix sum of 0 plus v of I. So v of I here is v of 0. Here v means the amount of fruits in our consideration, right? So here we have 8. So 0 plus 8, this will give me 0. So I'll just write this array here as well. So we have 8, 3, 6. So this is just the amount of fruits, right? I've just written 8, 3, 6 here. So which is our v array, the value array, right? So that we get here. And prefix sum of 2 will just be prefix sum of 1 plus value of 1. So that is 8 plus 3 is 11. And here the same thing, prefix sum of 3 is equal to prefix sum of 2 plus v of 2. So that will give me 17. Now you might think, bro, why is this prefix sum array so useful, right? Now let me give you the same question. Let's say I've started at the 0th index and gone all the way up to the 2nd index, right? Now for you to tell me like in this fruits array, like how many fruits I have collected, you literally go all these indexes and add them all up, right? So starting from 0 and going up to 2, you would add up all these indexes and tell me the amount of fruits that you collected. So you tell 8 plus 3 plus 6 is 17, right? But to get the same value, so let's say we have to get the range sum between the start and end value. In our prefix sum, it's very simple. You just do ps of en plus 1 minus ps of start, right? So here you had to do 3 addition operations, but here in this prefix sum concept, so we just need the same thing, 0, 2. So ps of 2 plus 1. So ps of 3 minus ps of 0. Right, start is 0. So ps of 3 is what? 17. ps of 0 is what? 0. So 17 minus 0 is 17, right? We got the exact same answer in both places, but here I just deploy the subtraction operation once, and here I did the add operation 3 times. Now if you have a million intermediary fruits, right, you in the normal case, if you're just adding up, you'll be adding a million times. In the prefix sum concept, you're just doing subtraction once. So initially at the start, you do this million addition operations, but every consecutive time after that, you're just doing this prefix sum subtraction concept once, right? Just one subtraction you're doing. So this is how it becomes very useful, especially in this problem, right? We're going to do a lot of combinations of these fruits, and we're going to add them up. So this prefix concept is going to make it really easy. So this is going to be our first takeaway. Do the prefix sum concept. Okay, now we are very close to the core logic of the problem, but before that, let's just look at one thing, which is what is the best possible path across a certain number of fruits, right? So here, for example, let's say here left stands for my first fruit and right stands for my last position of the last fruit in a consideration, right? Now, again, I'm clearly telling here, which is I'm focusing on the position of the fruits, because we have broken the concept of using just steps, because unless you reach a fruit, your number of steps doesn't matter, okay? So now, let's say I'm at this start position, right? what is the minimum number of steps that I can take to cover all the fruits in these segments, right? From the right fruit to the left fruit, right? So there may be fruits in middle, right? So what are the certain possible paths you can take? You can go one step to the right and then one step to the left and so on and so forth. See, this would be the worst possible sort of paths you can take, right? So now, one way you can do this is going all the way to the right and then going all the way to the left, which is very sensible to do, right? So instead of 3, I'll call it 2 here, and instead of I'll put somewhere around 8 here, right? So now is going to the right and then going all the way to the left a very efficient way to do it. So going all the way to the right would be 8 steps here, and going all the way back to the left would be 10 steps. So 18 steps. Is there a very better way to do this? Definitely. Instead of going to the right first, you go all the way to the left first. So go all the way to the left and then go all the way to the right, right? So by going all the way to the left first, you're taking 2 steps, and then going all the way to the right, you're taking 10 steps. So total 12 steps you're taking, right? So what you do is go to the smaller end first, right? And then cross the whole line segment. So how, so this would be, the whole line segment would simply be right minus left, which is the length of the whole line segment. But then you also want to find out to go to the closer end first. And how would you get the closer end? Oh, it's very simple. Minimum of, so you have start minus left, comma, right minus start. That's it. So minimum of your right minus start and start minus left would give you the closer end, right? The value of the closer end. So let's just to prove it, let's take the same equation in this line. I want to tell what is the minimum k value between where I cross all these fruits, right? So right minus left, so that would be 10 minus 0, which is 10 here, and so start minus left is 8 here, and right minus start here is 2, right? So minimum of 8 into will give me 2. So 10 plus 2 is 12, which is this path and which is the most optimal path you can take it to cover all of it. So this is the core idea here again. And now we're going to finally move into the core logic of the problem. It's going to be very simple if I understood things so far. So this is the core logic of this problem, and in this problem we are going to use the sliding window approach. And here the window means the indexes inside your fruits array that are under consideration, right? And again, I told why the indexes and the positions of the fruits are more important than the number of steps, because the number of steps themselves don't have meaning unless you encounter a fruit, right? So here initially you are going to start at L is equal to 0th index and R is equal to the 0th index. So initially you're just considering the first, your window will just consider of the first fruit inside your fruits list. Okay. Now let's look at how the sliding window approach is going to work, right? So first we are our initial sliding window will always be the smallest possible window, the initial location, which is just 0, 0, right? So that is what we're considering right now. And now we have to use that as a window and calculate what is the fruits that we get. And okay, so let's just look at the algorithm, and I think that'll be better for understanding, right? So first we have to, when you're considering a particular window, you have to calculate the cost that it takes to cover all the fruits in that particular window, right? So now our start position is 5, right? Now our window is just this, both our L and R are at this initial location. So which is 0, 0. So the position here is 2, right? So now I have to calculate the cost that it takes me to cover all the fruits inside this segment, right? So how do I calculate that? Very simple, as we've already discussed. So you take the cost is equal to RP minus LP. So RP means the position at the right index. So right index is 0 here, and the position at the right index is 0. I mean, position at the right index is 2, and L is 0 here, and the position at the left index is 2 here. So now we get RP minus LP, which is just 2 minus 2, plus minimum of, here there's another addition, absolute of S minus LP and absolute of RP minus S. It's for a very simple reason, because at some points, right, both your left point and the right point will lie in one side of the start, right? So at that point, in those situations, you can't just use S minus LP and RP minus S. You should use absolute of S minus LP and RP minus S, RP minus S, right? So that's why this absolute is very important here. So minimum of, so we have 5 minus 2, and then so 5 minus 2 and 2 minus 5, right? So that is just 3. So we are getting a cost of 3 for this, right? So 0 plus 3, which is very valid, right? So from the start you travel 3 steps down this line and you reach the second position and collect all the fruits inside the first window, right? So my So now we have calculated the cost. Now we go to the next step. While cost exceeds k, what was the collected? What is the cost for us so far? Which is just 3, right? So 3 is less than 4. So I don't have to sort of think of shrinking the window right now. All I have to do is, yeah, it is a valid window. So at this point, what I do is update the max fruits. Let me initialize a variable called m, which is stands for my max fruits. So max fruits will initially be 0. Now my max fruits is what? The sum of the elements in this window, 8. And I already told you it's very simple to calculate the fruits inside a window because you calculate the prefix sum array. How do we do that? Value is equal to ps of r plus 1. So r here was 0 for us. So 0 plus 1 is 1 and minus ps of l. L was 0. So ps of 1 is 8. 8 minus 0 is 0. So I mean 8 minus 0 is 8. So our number of fruits in this first window is 8 and we have updated the max value. Okay, very simple. Now should we stop this algorithm? Definitely not, because we have not we have not gone to the rightmost index in our list. So again, you can even call this the len of fruits instead of 0 comma max, right? Okay. So now what we do is we have to expand this window. How do we expand the window? Very simple. Expand the window just means incrementing the r position by 1. Okay, I'm going to use red for this iteration. So now my r is at the first index and l is at the 0th index, right? So my r has shifted from here all the way to here. Okay. So now let's repeat the algorithm. Okay. Now first what we do inside the algorithm, first calculate the cost of traveling this segment from L to R. So how much will that be? So RP minus LP. So RP is given by 6 here. So 6 minus LP is given by 2. So 6 minus 2 plus min of ABS of S minus LP. So S is 5. 5 minus LP is 3. And ABS of RP minus S. So 6 minus 5 is 1. So this will be 1. So my total cost here is 6 minus 2, 4. 4 plus 1 is 5. So my total cost here is 5. And it's very easy to see. That means I travel from here all the way to 6 and then travel all the way back to 2. So 5, 1 plus 3, which 1 plus 4, which is 5, right? Which is the cost I'm getting here. Now, but if you see in this situation, my cost is exceeding the k value, right? If my cost exceeds k value, this means that I cannot you consider this sliding window, because to cover this window, I would have taken more steps than the threshold allows. What should I do here is very simple. I have to shrink the left side of this window. How do you shrink a window? Just by incrementing left by 1. So my left also comes to my second index here. Right, then I repeat this algorithm. So I will get my cost here as, I'll just calculate it right away. So it means just I'm traveling here once and collecting all the fruits here. So my new cost is 1, right? And then my new value is what? All the fruits in this location, which is just 3, right? But in this position, if you see, my value 3 is less than the max fruits that I have, so I don't have to update the max fruits, right? So now we have completed these steps. Then finally, we again increase the right side window. So right side window will go up to this location now. Okay, now we repeat the same process. First, I calculate the cost taken to cover this window, which is just cost of RP minus LP. Cost of R minus L is what? So 6 minus, 8 minus 6 is 2. So 2 plus min of absolute of S minus LP. So absolute of 6 minus 5 is 1. And absolute of R minus start is 8 minus 5 is 3. So absolute of what is the minimum of these two values? Obviously 1. So 2 plus 1 is my new cost, which is 3. And it's very easy to see how that happens. I'll just write this all in green. So that means I'm just traveling once all the way to this 8, right? So I've covered all the fruits in this segment where L is here and R is here. Now I have to calculate the value of these fruits, right? Value of the fruits is very simple. So that is just PS of R plus 1. R here is 2, right? So PS of 3 is what? PS of 3 is 17. So 17 minus PS of L. L here is what? L here is 2, right? So 0, 1. No, L here is 1, sorry. L here is 1 because it's referring to the index in the fruits array. So PS of 3 minus PS of 1 is equal to what? So we have 17 minus 8, which is equal to 9. 17 minus 8, which is equal to 9. And as you can see, 9 is greater than my max value of fruits, so which is my max value of fruits is updated, and now I can just update the sum. Okay, I mean update the max fruits, which I'm done with. And have all my windows been checked here? Obviously yes, because I cannot push the right anymore to the right. So this is how the final solution of my problem is obtained, which is 9. So this is going to be the code for my problem. It's going to be really simple. First, what we need is just the prefix sum part. So n is equal to len of fruits, right? And then I have to create the empty prefix sum list. So prefix is equal to n plus 1. And then I have to just populate this prefix sum list. How do I do that? Very simple. For I in range of n, ps of I plus 1 is equal to ps of I plus fruits of I of 1. Now why I of 1? Because I'm searching for the amount of fruits and not the position of the fruits when I'm adding it to the prefix sum, right? Okay. Now let's go to the sliding window aspects. So first L comma R is equal to 0 comma 0. Initially both left and right pointers are at 0 comma 0. And then what I need is my max fruits value. Max fruits will initially also be 0. And now let me just extract the positions individually of the fruits and place them in another list. It's going to make my writing very simple. You don't have to do that, but it just makes my writing very simple. So fruit of 0 for fruit in fruits. Okay, got it. Now we move to the code sliding window algorithm for R in range of n. So for R in range of n, this part automatically takes care of increasing the window size for each iteration of this loop. Now inside this loop, the first part what we are going to do is check the cost. So cost is equal to, so P of R minus P of L. So now you can already see how the extracting the positions made my writing very simple here. Instead of writing fruits of R of 0, I'm just writing P of R. Right? Plus minimum of absolute value of start pos minus P of L, comma, absolute value of P of R minus start pos. So this is how it's going to look. Formula is really simple. P of R minus P of L plus minimum value of absolute value of start pos minus P of L and absolute value of P of R minus start position. Why absolute values in both cases? For a very simple reason, because in some instances both your left and right pointers will lie on one side of the start position, which will throw your algorithm off. So you always need the absolute values taken. Okay. Now we have to check if the cost is not valid. We have to shrink the window. So that's what we're going to do now. While cost is greater than k and L is less than R. So we ideally just want to shrink the window as until the L matches the right pointer. If L is going beyond the right pointer, it doesn't make sense that we are going to shrink it beyond that. Okay. So L plus equal to 1. And we're going to do the same thing here. Right? We shrink the window and recalculate the cost. Right? After this, hopefully your cost will be valid, but it's still not 100% sure that your cost will be valid, because there are some cases where no matter where your how long or where your sliding window is, you'll never have enough k to reach that point. So all the costs will be invalid. So we definitely have to check if cost is less than or equal to k. Only then we can update our max fruits. So max fruits is equal to max of max fruits. Okay, now we have our right and left pointers, but how do I calculate the sum of fruits within that window represented by the right and left pointers? Very simple. That's why we calculate the prefix sum list. So it's going to be ps of R plus 1 minus ps of L, right? And all you have to do now is just return off max fruits. Okay, there is one slight improvement you can make to this algorithm. Instead of just doing L plus 1, you can do a binary search and get very quickly to the position that you're searching. You can maybe try that and tell me in the comments how would you go about doing that. Okay, and one thing to take away from this problem is hard problems are not essentially hard because you don't know the algorithm or something. It's very something that you've never heard of. But there are a lot of instances where a hard problem is just a coming together of many concepts like this. So today we use a prefix sum concept, we could have used a sliding window concept, and then potentially binary search was also an option here to improve this algorithm. So this is how we solve this hard problem. I'll also update the Java code, the JavaScript code, and the C++ code in the comments. And if you have any doubts, please feel free to ask. I would read them and love to respond to them. I'll quickly see you with another video. Until then, take care and goodbye.